All right. Hi. It has been a while since I have made an official video. I think the last video I've made content-wise, I think it was the final review session from last semester because I made a lot of these videos last year and there are a good amount. So if you're trying to study for the final, watch those videos. But I think as we move on, there's some topics that we are covering between test three and the final that a lot of people struggle on, right? And that's going to be your aldol and Claisen condensation. And why is that? Well, because we're dealing with more nucleophilic carbons. And that is an entirely big new thing for us to unpack. Like we've seen some nucleophilic carbons like Grignard or um yeah, yeah, Grignard is probably the best example. But when we're dealing with aldols and Claisen, we're dealing with some relatively new content, but all in all, a lot of the explanations rely on resonance that explain it, okay? And not only that, it's such a big concept in biochemistry and on the MCAT. So if you're trying to take a medical admissions test, or you're going into like a biochemistry related graduate program, you're going to be dealing with a lot of aldol stuff because aldol chemistry is particularly important in carbohydrate chemistry, right? Aldehydes, ketones, alcohols, all functional groups that are very present in our carbohydrates. Now, that being said, I think I'm going to go ahead and move on to the actual bread and butter, okay? Let's go ahead and share the screen. Okay, we are going to resume, allow, perfect. All right, you should be seeing my screen right now. Okay, so first off, what we're dealing with is going to be an aldol, all right? Just an aldol. Now, for an aldol, the name pretty much derives from aldehydes and alcohols because initially we thought that this reaction just happened between um, your carbonyls, which produces an aldehyde and an alcohol. But we figured out that ketones pretty much do the same things as well. Ketones also have acidic alpha carbons, and we can also have ketols. But this is just an all-encompassing term, aldol. So, like I said, this is going to be your aldehydes and ketones, right? Now, what about carboxylic acid derivatives? Well, when we deal with carboxylic acid derivatives, that's going to be Claisen condensation. That's going to be a different thing, which we will get to. So essentially, let's say we had an aldehyde, right? Propanal, and we had acetone or propanone. Well, if we were to combine these, we would get a structure that looks like this. Now you might be thinking, what the heck am I looking at? Right? We have an alkene and then a ketone or just a general carbonyl. Well, what the heck is happening? Well, in short, I'm going to give you a summary and then I will explain it. Don't worry. We have a nucleophilic carbon attacking the electrophilic carbonyl. It makes a bond, kicks off the O in the form of an OH or water, and then it makes a double bond. That's essentially what we get here. But I'm going to go ahead and show you guys a quick shortcut that I like to do. So all you do is grab whatever electrophile you have and just move the alpha carbon over it and paste it like that. And then they're going to be identical. And that's your answer, right? So if you here, let's backtrack. If you were given, okay, what is the aldol product of this? And you are not seeing this at all. You have to find the product. Well, if I know that between aldehydes and ketones, aldehydes have the alpha carbon that's more acidic. If it's more acidic, then it's going to pop off that proton and it's going to be nucleophilic in a basic solution. So whatever nucleophile I have, that's basically what I'm going to paste over the O of whatever I had left over. I might be thinking, well, that's not sufficient. It might work on the final, and that's probably what you're going to do on the final. Um, let's actually get to the nitty gritty. I'm going to pause this real quick and get my things. Whoops. Right, I should be back. My recording? Perfect. Okay, like I said, for your aldehyde and your ketones, you're basically going to add whatever alpha carbon that's more nucleophilic on whatever carbon you have where that electrophile is. Now, I just spit a bunch of stuff at you, but let's break it down. So whenever you have a ketone, let's redraw that ethanol, for example, right? H. Well, whenever you have a basic condition, so let's say this was under basic conditions, so let's say we had LDA. Under basic conditions, you have a hydrogen here. And as we know, the hydrogen is going to be very, very acidic, or compared to normal alkyl hydrogen, which is a pK of around 50. This one's going to be relatively more acidic. I think it's like pK of 17. I don't know off the top of my head, but it is going to be relatively acidic. So if you have a strong base like LDA or even NaOH, it's going to pull it off. So when we pull off that proton, let's say we had LDA, right? Snatch up that proton. Electron's going to go here, electron's going to go there. And then we get our enolate. There we go. And that's a very important term. So we started off with some kind of carbonyl. I'm just going to call this the keto form. The intermediary between the keto form and the eventual enolate form, which here, let's go ahead and draw that here. It's going to tautomerize between the two, the keto form and then this enolate form. Let's see right here. Oops. OH. This is going to be our enol form. So it's going to be mainly these two that exist in the solution for most of its life, and the keto form is going to be highly favored. But again, when we have stuff like LDA, we can push it to an enolate form. Enolate form. And the enolate form is very notable because there's two main resonance structures, right? The one that I just showed here, which forms initially right after the LDA snatches the proton, and then you have this form, which is how I kind of like to see it. You have that H from there, and the lone pair there, like that. And the reason why I like this one in particular is because it's like the carbonyl form that we started out with here. But we just added the protons. We just took off the protons, and then it becomes something like that. And that's what we have right here. So if I were to draw this, right, if I were to draw the enolate form, it would just basically pull out that proton, and there we go. And you might be thinking, well, why is the enolate important? Okay, if we pretty much only care about the enol form, the carbonyl form, when we're dealing with how we're drawing it on a piece of paper, what does the enolate do? Well, the reason why the enolate is so very important because the enolate is the one that's nucleophilic. Right? When we have the enolate in this form, this is going to be the nucleophile that's going to add to other things. It's going to add to carbonyls in carboxylic acid derivatives, which is a type of Claisen condensation, or it's going to add to carbonyls of other aldehydes and ketones. So with the knowledge that this is going to be nucleophilic, we finish that first, or we cover that first facet that I described, okay? Whatever acidic alpha carbon you have is going to become the nucleophile. Why is that? Because whichever one's the most acidic alpha is going to be the nucleophile. So if we were to backtrack from our original equation, the very simple one, these are going to be our alpha carbons, okay? These are our alpha, 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 alpha. Whichever one is most acidic, this one for an aldehyde, that's going to be your nucleophile. And that's the one, again, we're going to paste over like this, right? Now, let's backtrack one more time. I know I'm like stuttering like a broken clock. Like, okay, we've backtracked a whole bunch of times. Well, I want to make sure we cover this. How do I know an aldehyde is more acidic than a ketone? Well, you can take me and Dr. Berg's word for it. It just is. But let me explain it. For acidity, aldehydes are more acidic and more likely to be nucleophiles than ketones. And let's draw it out. So if we have an aldehyde, let's bring back that ethanol. Bring back that ethanol versus our propanone. Yeah, let's keep it simple. There we go. Here, let's make it like this. Two, like that. Well, it goes to show that this proton, that alpha proton, and this alpha proton, let's go ahead and keep our labels alpha, alpha. This is going to have pKa of around 17. This is going to have a pKa of around 20. So this is 3 magnitudes, or 10 to the 3 times more acidic than a ketone. Why is that? Well, the reason is right here. Whenever you have a ketone, you're going to have an R group on the other side. But for an aldehyde, instead of an R group, you have an H. And H is on the other side, and over here you have some kind of R group. And if you remember from the chart from test 1, alkyl chains are higher on the list, while H's are going to be neutral and electron donating. Aromatic groups and alkyl groups are electron donating. So in actuality, we have something like this happening. We have something that's electron donating. And since propanone is symmetrical, you could flip it around. It's the same thing. Don't worry. You have some kind of electron donating. So this is going to be not as electrophilic. And whenever you have this enolate, for example, if this was an R group, you would have electron donating regions to that resonance stabilized anion. So because you have the R group in the ketone, it's not going to be as nucleophilic. Moreover, steric hindrance, all right? So ketones, electron donating, which destabilize, emphasis, destabilize our resonance stabilized carb anion, and steric hindrance. Whoops, not striac hindrance, steric hindrance. That was not, I'm so sorry about my handwriting, you guys. It's been a long semester. Hindrance. Steric hindrance. All right. So now we're done with that. Let's go over like a quick little example, right? Let's say you had something like this, H. And then we're going to add this ketone. All right. If you were to react both of these with an LDA, which one is most likely going to be the nucleophile and add to the other? Well, knowing your rules, this one, this alpha carbon is going to be a lot more acidic because it's not as sterically hindered and it's not as destabilized by electron donating groups. This is going to be more acidic. This is going to be pulled off. So what I would like to imagine is this, once we react with the base, is going to have that double bond right there. Not double bond, but lone pair. Is going to act as nucleophile, and we'll just lay it over there. Here, let me draw it a little bit different. I think I had pentagon 3 on. So if I were to react this, I know that the aldehyde is going to be more acidic, and I would just plop that right over there. And that's this kind of structure I would make. And you're welcome to draw it like that on the test. If you're right, you're right. But now let's backtrack. Okay, one more time. We keep backtracking. Now that we covered the acidity, why do we care about the lone pairs at all? So if we already covered that the aldehyde is going to have the lone pair, because if you react with the base, it's going to give off that more acidic proton. Well, look, you have a nucleophile, right? This is the enolate. This is the enolate. That is this right here, the enolate. The enolate is going to be in the nucleophile. And what do you know? We have a carbonyl carbon that's a very perfect electrophile. Well, look at that. When we have a nucleophile and then an electrophile, we just add it. So what we see is these lone pairs pretty much just come in and add right there. It adds there. So what would we see? Well, let's draw that electrophile as it was. Well, now that the lone pair just added on, I think it's like this. 1, 2, 3, 4, 1, 2, 3, 4. Okay, now that the lone pair is added on, These are going to be kicked off. And then this is the compound we're going to make. Okay. Well, eventually that OH is going to be protonated into, I believe, OH. All I know is that the carbonyl oxygen that was added is eventually going to is eventually going to leave. And when it leaves, I believe it is this proton. Yes, it is. This proton. That base will come back, take that proton, make a double bond there. This is going to be your mechanism. Here, let me redraw it upside down. There we go. Now you might be thinking, well, why does this leave? Right? Because we know that OH is going to be a very bad leaving group. So why the heck does it leave? Well, it leaves via an an E1 like elimination. And that should make even less sense for you because well, in E1, you get a carbocation, right? So if a carbocation, your leaving group leaves carbocation, how does that work in a basic environment? The answer is it doesn't. This type of E1, remember, our types of eliminations are going to be E1, E2. The one we have is going to be an E1CB. That's an E1 conjugate base type of elimination. Now, we don't expect you to know that. That's just something that we know. And the reason why that exists is because when we have a resonance stabilized anion like this, you have an electron dense leaving group, an electron dense region. Well, when you make this enone, you have enough energy to just kick that off. Right? Basically, the electron density of our resonance stabilized enone conjugated system is enough to kick off the OH in a basic environment, which is fine because it works out for us. We get an enone, right? So let's bring back the original thing. Well, if I know that whatever I have, let's start from here. Hold on, I drew that wrong. I'm just redrawing what I have over here. My aldehyde and my pentan 3-one. If I were to react it with LDA, well, all I would do is, okay, identify which one is more acidic. Well, I know that out of my alpha hydrogens right here, the one in the aldehyde is going to be more acidic, it's going to be more electrophilic. It's going to plop on right there. So if I were to redraw that, here, let's do this. Doing that little trick, just do that. And then I do this. That's going to be my product. And lo and behold, that's what we have right here. Right? Look, it just overlaps. That's what we have. That is what we have. And you can draw it any way you need. As long as you get the idea, that's what works. And let's bring it back over here. Okay, we had propanal and then propanone. We react this with a large strong base. Okay. Our nucleophile here, there. And then we're going to get something like that. And then we get something like this. Bam, that's all you need to know. Now, let's try to see if we can apply this on da-da-da-da. Oh, not that. This one. Look at that already. So right now, what I can see right here, we have one right here. Look, we have a strong base. We have an aldehyde and another aldehyde. So now let's break it down. So the first step when you're doing an alcohol is first off identify, okay, I have an aldehyde and aldehyde, or an aldehyde ketone, blah, blah, blah. If my reactants are only going to be aldehydes and ketones, it's going to be an aldol reaction. Excuse me. Let's identify our acidic carbons. Our acidic carbons are going to be right here. And that's it. Now, why not the other one? Well, first off, this one, there are no protons. That's sp2. This one isn't even a carbon. So if there are no analyzable protons, then what we can essentially just do is this. Draw our electrophile, right? But instead of that O, let's just stick this entire portion on. There you go. And that's your answer. It was that easy. Crazy, right? Crazy. That was crazy ones. Okay, now let's get to the next bit. You have thermodynamic versus kinetic enolates. Now I'd be thinking, well, what the fuck, right? If I have a thermodynamic and a kinetic enolate, what does that mean? Well, let's say you had something like this. Okay, you have a ketone, so it is asymmetrical. You can't just rely on the aldehyde being the most acidic. Let's say you had a ketone like this. Well, now what do you do? Which of these? You have two alpha carbons, alpha, alpha. You have a proton here, proton there, proton there. You have two alpha hydrogens or carbons with three total hydrogens. They're all equal in acidity, but one of them is sterically hindered, one is not. So what do we know? Well, if you remember your conjugated dienes, right? You guys remember that? Your 1,2 addition, 1,4 addition, thermodynamic and kinetic product. The same kind of logic applies here. The less substituted is going to be the kinetic. Thermodynamic is going to be the more substituted. This is going to work at colder temperatures. It's going to be irreversible and just generally unstable. Generally less unstable because it's less substituted, right? When we draw out the energy diagram, we'll see why. And then for the more substituted, it's going to go forward at a higher temperature. It is reversible and it's very stable. And it's very stable. Why? Because it's more substituted. So let's take it over here. So off the bat, I can already tell, okay, I have a tertiary and a secondary. Right? If I were to describe these alpha carbons, they're going to be tertiary and secondary. So I know this is going to be our thermodynamic. This is going to be our kinetic. So if I were to draw the energy diagrams, this is what it would look like. For the thermodynamic, it's going to look something like this. This is going to be that kinetic enolate. But for the, or not kinetic, the thermodynamic one. But for the kinetic, over here, it's going to look something like this. Yeah. So we can see that right here, we have let me use a color. It's going to have a higher activation energy, thus it needs a higher temperature. But the bigger investment in the energy, the bigger return, because we have enough energy to go to the more sterically hindered alpha hydrogen. We have enough energy to remove that. And then we ended up having a more substituted alkene. But over here, we don't have a whole lot of activation energy because if we're at a colder temp, it's going to go to the easiest one. This is going to happen the quickest. It's going to happen the quickest because if you don't have a lot of energy, you can't have enough energy to do the thermodynamic product. So the only way you can go is to the more sterically available and quickest, less substituted kinetic product. All right. And it's going to be less sterically hindered, going to be less stable. Granted, it can still happen, but if you just look at just internal energy wise, it's going to be less stable, less secondary, and less tertiary. So how do we apply this? Well, let's look over here for these ones right here. What am I looking at right here? Right here. And pretty much I see the same thing. Okay, I have LDATHF, LDATHF. This one's at a relatively higher temperature. This is going to be a relatively lower temperature. So let's complete step one. Step one, I'm going to keep it in black. Step one, I'm going to remove the alpha hydrogen at a higher temp. So it's a higher temp. Well, out of our two alpha carbons, the one that's more substituted is going to be thermodynamic. So we're going to get something like this. Everything, well, Patrick, that isn't what you drew over here. That pretty much is, because remember, there's going to be resonance, right? Resonance, that's our enolate. Okay, same thing. All right. Now over here, if I were to do the first step, LDA-THF at -78, I was going to have something right like this. Okay. Now for the second step, we're reacting a carb anion with an alkyl halide. And what do we know about this alkyl halide? That's going to do an SN2. It's going to do a backside attack, kick off the bromine. So essentially what we're going to do is going to have something like this. Our nucleophile is going to be this one. You need to add that there. We basically did an SN2. And if you're thinking like, Patrick, how the heck did you do that? What is an SN2? Hate to break it to you, but you should know SN2. Now over here, what if we were to do the SN2 over here? Well, let's break it down. Let's do it. If this were to add to our CH3, CH2, Br, it would add here, kick off the or not the protons, the electrons here, and we would get something like this with a Br in solution. I'm not going to write the Br, but you know it's there. Hence, I'm going to double check, make sure I kept my carbons. All right, I added 2 carbons total, and I retained the original 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I retain my carbons. I'm all set. So I at least know, oops, confidence in this one, thermodynamic product, and our kinetic product. And then we have our aldol right here. Look at that. Look at that. We're gonna do the same over here. That's the same, that's the same, that's the same. We just did. That's the same, that's the same. Ooh, let's do this one. All right. Okay. We have a similar situation. Okay, if we had the two, okay, let's look at our alpha carbons. This is alpha. This is alpha. But the alpha, even though it exists, it's sp3 hybridized. It's only connected to other carbons. There are no protons attached to it. So we know that this is non-enolizable. That's non-enolizable. So we know that this is going to be the only nucleophile we're going to have. All right, NaOH is going to come in, swoop in, take that proton, and create our nucleophilic enolate. And this is going to come in and attack our beloved electrophile and is going to do the entire mechanism. And that's just how we can imagine how the mechanism works. But let's just visualize it, okay? If I know that this is going to be our electrophile, let's just draw the electrophile. And then whatever thing we have here, let's do red. Our nucleophile, we're just going to add it there. We're going to remove the O, and whatever nucleophilic carbon I have is what I'm going to put here. And that's pretty much it. I essentially just took this and I plopped it over here. And this is a perfectly acceptable answer. That's what you can do. That's what you can do. Okay. Let's go ahead and I guess we can go ahead and do some of these. I think I'm going to save the Claisen for a different day or a different video, but we can probably knock some of these out already. I think you guys might appreciate that. Okay, so let's go ahead and tackle these. So for Grignards, whenever you have an alpha beta unsaturated ketone, actually, wait, I think there was something I was missing. Hold on, I think there is something missing. Not for this, but something I did want to talk about. Oh, yes, there is something I wanted to talk about. Perfect. I'm so glad I remembered. Serious selectivity. What if you were to add these two, right? That kind of sucks. Why is that? Well, that's because, look, we have two ketones. We have two ketones, so we can't really automatically just pick the aldehyde to be our nucleophile. And not only that, but this one's going to be asymmetrical. So these are the ones I colored in red are going to be valid alpha carbons and their respective alpha hydrogens. But that means we're going to have different products. Granted, we might have a major product, but we're going to have a lot of products. I can see a possible four or three, at least three different types of products. And they might be in relatively significant amounts. Like, even though our major product might be like 55% of our yield, the other 45% might be the other two that we don't really want. And practically, that's just BS. We don't really want to do that. So, a very common technique is get something that's non-enolizable, like we saw before, something that is still an electrophile, still has the carbonyl, but does not have any alpha protons. We saw before, benzaldehyde is a very, very common one. There are no alpha hydrogens. It has one alpha carbon, but it's going to be sp2. Or terbutylaldehyde. Same deal, right? No alpha protons. So if we were to take this out of the picture and react to one of these, which we saw in those problem sets, well, we know, hey, whatever proton we or nucleophile we have here, we can clearly say this is going to be our electrophile, and our nucleophile will add there, and we'll create that product. And if I were to complete this out, I'm going to draw my electrophile and basically just replace this with this. Here, let's get all of it. Here, let's get all of it like that. And I would redraw the product because I just did it visually. H. There you go. That's what you would do. That's perfectly acceptable. Okay. All right. Let's bring it back. Let's bring it back. So when you have Grignard reagents, Grignards are going to be very strong nucleophiles. And when you have alpha beta unsaturated carbonyls, they're going to add to the carbonyl. We'll elaborate a little bit more on the alpha beta unsaturated, but I think we can knock this out here because it's something we covered relatively early on into the everything, as in we covered it yesterday and Monday. Strong nucleophiles, like these carbanions, are going to attack to the carbonyl. Okay. Why? Well, here, let me go ahead and draw it here. When you have a unsaturated, here, let me use this example down here. The prop or the cyclohexenone. Let's use this one. If we have a electrophilic carbon here, this is also going to be electrophilic. All right. It's also going to be electrophilic. Why is that? Well, you can, oops, not that. This is going to be partially positive, partially positive. It's going to be electrophilic. And by it just is by resonance. You can draw the mechanism, but you can just take my word for it. This is going to be our 1, 2, 3, 4. 1, 2, 3, 4 additions. Strong nucleophiles are going to do the 1, 2 addition. And then weaker nucleophiles are going to add to the 4 position. So when we have a strong nucleophile like this, all we have to do CH3, this is kicked off, and we're going to replace it with CH3. That's the first serving of our Grignard. And then since this is in excess, we're going to do it again, where we're going to kick that off and put the proton or the electrons here and have another CH3. And then with this H3O plus, we're going to protonate this, and this is going to be our product. Now for here, you can take my word for it. These organocuprates are going to be our softer nucleophiles, and they're always going to add to the 4 position, or the I say relatively 4 position. This is going to be your beta, alpha, beta. They're going to add to the beta position. You're welcome to just take my word for it. They're going to add to the beta position. Is all we have to do. You don't have to overthink it. You can just take my word for it. Hopefully, I've been a trustworthy source for you guys recently, so please just take my word for it. Now let's get to these. Cl2H3O plus. Well, we know that Cl2 is going to add, in this case, it's going to be an electrophile. It's going to add to the alpha carbon. And we only have one alpha carbon here, so I know if it's going to add, that's all it does. It just adds. Cl, C. And the thing is, if it's acid catalyzed, it's only going to add once. So this is my final answer. But hypothetically, throw me a bone. If this was NaOH in a basic solution, it's going to add twice. Okay? It's going to add twice. For this one, we're going to CH3, CH2, COH. Now, this is just going to do the same thing. It adds to the alpha. Even on a carboxylic acid derivative. It's just going to add. So we've already pretty much knocked out, what is that? 7 out of your 10 problem sets. Maybe I'm biased because I'm group 1, but honestly, these are pretty much the same. Oh, perfect example. Look. Cl2NaOH is going to add twice. It's going to add twice and do this. Why is that? Don't we have a phenyl group? Well, the phenyl group is going to be beta. We still have the alpha here as base catalyst, so it's going to add twice. It's going to add twice. Yeah. Okay, cool. I think the rest I might cover in a later video, but I think this is a very good first step to hopefully get you guys moving forward, all that.